Okay. So this is today is lecture 4 for this course. Lecture 4. So we would be continuing what we had discussed. So let me go back to the first fundamental form. So first of all, surface of evolutions entities. Yeah, so essentially the goal of the first fundamental form is to understand or to quantify measures on a surface. So it's as if, say, we want to find a distance. So we have any arbitrary curve. We want to any arbitrary surface. We want to, and
Sorry,
just we say impose.
sorry to interrupt you, but in case if you have shared your screen, that is not visible to me.
Okay, okay, but okay. Let me. Okay. Let me reshare it. So is it visible now?
Yes, it is visible now.
Okay. So the idea is we have this any arbitrary surface and we overlay or we impose some curve which lies in the surface itself. So it follows all the contours, all the variations, all the gradations which are in the surface. So we would like to determine the distance along the curve. So the distance from here to here as you follow the curve. So that's what the what do you call the intention or the aim of the first fundamental form is. So we use first fundamental form to be able to uh, define some sort of a measure between the endpoints of a curve lying in a surface. As an example, like we had this last time. So say we have this curve which lies between on the surface, and we have some in its starting and end point. And of course, since the way we measure a curve, the length of a curve was that we would be varying the parameter along the curve and then taking the magnitude of its tangent, the magnitude of a tangent vector, and then integrating over the parameter, which is t. Right. So which means that since curves are essentially 1D object, although they are embedded in 3D space, but in general, it's always a 1D object. So which means that integration has to be done along that particular direction or uh, along that particular parameter. So since t is the parameter, we integrate along t. But if the curve lies on a surface, then we see that surface are themselves 2D, they are defined by 2D parametric space. But because of the virtue of curve being 1D, so we would want to follow along the curve. So what we do is we move back, we take a step back and define some sort of a t parameter and then map it to UV for the parametric space of the surface. And then uh, so to speak, we are defining the curve based on that. So it means that if the surface was sigma UV, then U and V will both be a function of this t, which is the parameter. So it means that we are able to trace a curve on the surface. And then we use the standard length formula to be able to determine the the length, so to speak, of the curve. So what we see is during in this process, we see that we have this some sort of a dot products between two different quantities, and these quantities happen to be the basis vectors. So which means that they are basis vectors at any point on the surface, right? So later we will come to know that sigma u and sigma v are both what we call as the covariant basis vectors. And they vary from point to point, since the surface is essentially we are on the 2D parametric space, and when we sorry, map into 3D, then we have this curvilinear coordinates, right? So, and at every point along this we'll have this two tangents, which are functions, which are just the derivatives with respect to the parameters, which is u and v for a surface. Right. So in this case, we are able to get these three dot products: sigma u dot sigma u, sigma u dot sigma v, and sigma v dot sigma v. And then we call these quantities as E, F, and G. And what we see is that E, F, and G only depend on the point at which the derivatives are taken, point P, say. They only depend on the point V, and doesn't matter how you approach the curve, whether the curve happens to be like this, or any such, but it should just pass through this point P vector. So which means that this E, F, and G are point, what do you call, they do not depend on any curve per se on the sphere, but they will only vary from point to point, right? So, so which means that E, F, and G are unique at every point. That's the whole aim of saying this. So now we saw that we could use it to determine the lengths. So even when we determine the length, this E, F, and G comes into the picture. And what we do is we give this special name. So this form we call as the first fundamental form, right? And we learned that such fundamental form can be used to determine lengths, of course, and it can also give us the angles of intersection between any two curves, right? So in this case, say we have gamma vector and phi vector as two curves. So for every curve, we determine the first fundamental form E, F, and G, and then we could determine the angle of intersection, or the angle between the tangents to both the curves at this point P, using the coefficients of the first fundamental form, right? And then later we went to a special type of deformation, what we call as the isometry, what are essentially called as isometry. So isometry are the distance preserving deformation, right? So I should have called it. This should not be like that. It should best this mapping is called as isometry, and they are isometries are distance preserving transform distance preserving deformations or mappings, if we can. So from an engineering perspective, or say from an applied mechanics perspective, we would always like to use the word deformation, because we see surface as some sort of a very thin body, which is, as you apply loads over it, it deforms. But mathematically speaking, they represent a mapping from one configuration to the another configuration, right? So if this phi maps from here to here, so let me call it a bigger phi, right? If this maps from this to this, then this, and if it ensures that the distances between any two curves, so this distance, right? So it's like this distance should be any two curves, not only for specific curves. It can be any curve, any arbitrary curve. This A prime B prime will also be, right. So double prime B double prime, right. So it should be between any two arbitrary points on the surface, right? So this leads to what we call as, then such surfaces are called, I mean, such mappings are called as isometric. And what happens is you'll ask, okay, but what is the use of isometry? Like I have been talking about distances, but you know that it's tough to measure distances. Say, I mean, from a physically speaking, if you are deforming one thin surface or thin elastic sheet, right? Consider this to be some thin elastic sheet or some say polyethylene sheet. Now, if you deform it, it's very it would be very difficult to like measure since you won't know where the point the curve after the pre-existing curve in the reference frame goes after you deform it, right? So there is an equivalent to isometry. So isometry, if mapping is an isometry, then it also preserves what we call as area. It also preserves area. Let me just open and mute maybe here itself. So isometry also preserves area. Isometries preserve area as well. So you'll ask, but how is it possible, right? So we have this surface and we take some, again, let me line it up with the special coordinate lines as we call it. Right? So let this be u coordinate lines and let this be v coordinate lines. Right, so I should call it u varies this way. So let's take some special cases u0, u1, and this in this way v varies. Okay. So let's take some special cases v0, one particular, and let me just color it up. So this patch will be, this is the patch we are talking about. Now, if if we allow it to say map it to another such deformations, right? Say something like that, and I'll take pains to have the same coordinate lines. Right? And let's mark the equivalent. So u0, u1, and v0, v1. So we are talking about this patch. And say phi is isometry. Then what happens is if you would call as this as S and this as maybe phi of S, right? Then what happens is the area of this patch. So the area of we can call this patch as sigma. Right? This is a sigma patch. And this patch here will have A, and I'll just call it phi of sigma. Right? So if since phi is isometry, then this implies that the area will also be preserved. Right? So the A is, this is the area just some area measure. And we know very well that, and of course, if that is the case, right? So what happens is uh, the way we define area. So area is defined as area function is defined as, say you have double integral over say sigma u cross sigma v into du dv. Right? So u is equal u0 to u1, v0 to v1. Now you can ideally what we would have is the most basic way we define an area is just double integral of dx dy. Right? That's the most basic explanation of how we define an area. Just double integration from some x0 to x1 and y0 to y1. Now in this process, as we had learned in multivariate calculus, that if we are transforming from say x is equal to uh, x of u comma v, and y is equal to y u comma v. And during this transformation, what we had learned is, if you recall, that dx dy is equal to some sort of a measure, say x comma y divided by partial u comma v, and du dv, right? And this you learned, we always used to map between two different spaces by something called as a Jacobian. Now, ideally, this is just a shorthand way of writing it, but we would, in expanded form, this is how it looks like. So which means that dx dy is a small patch and du dv is a small patch. So of course, this need not be of the same area. Let's have some sort of a this. So this Jacobian j here will multiply with du by du dv to give us the what do you call the area in dx dy. So that's what we are meaning. So small element in dx dy is related to small element in UV plane with due to this j factor here. And the way we would define it is we would take parcel x by parcel u, parcel x by parcel v, parcel y by parcel u, parcel y by parcel v. Right. So the determinant of it, this is called as Jacobian. Right. So similarly, in this fashion, we were able to do the same thing here as well. Right. So in that sense, what happened is sigma vector is it just gives us what you call as sigma. It's of course a vector, right? So it represents x, y, z actually in 3D space, and all of which are functions of u comma v, and then y is equal to u comma v, like z also u comma v, right? So here what we did is, and here mind you that it's not just coordinates, we are not mapping just from unlike in this case that I was showing for XY, we are mapping from 2D to 2D. Now in this case, we are mapping from 2D to 3D, right? So here, the way of, it's inspired from this only, it's inspired from multivariate calculus itself. So what we do is, let me go into a very fundamental level of, let's try to understand this. So say you have this, uh, let me consider this patch here, right? Let me consider this patch and try to expand it, right? Slightly enlarge it. And just for exaggeration purposes, let's just enlarge this patch and use the appropriate colors for the coordinate lines. So this is V, and this is V. These are the segment portion of the V coordinate lines. So what happens is, at this point, let's call this point as p vector, right? So this is the p vector, and at this point we could define the tangent vectors, right? So the tangent vector was this sigma u. This will not be sigma. This will be sigma v, because in this, along this direction v is varying, and along this direction you have sigma u, right? Now we recall that we try to gain the idea from uh, that area of a area of, say, any parallelogram, right? So in the if you just if you, what we do is, since in an infinitesimal space it would just resemble something like that. Since this is an infinitesimal element, it's very small, so you can just idealize it to some sort of a parallelogram. So this distance is dv and this distance is du, right? So the length of this is going to be, right? So this length will be equal to, this is just du, and this is going to be this is going to be du, and this is going to be dv, right? So what we do is, mind you, the way we used to find. So the length of this is in vectors. So I think let me bring to a new page so that you can understand things better. So say you have a parallelogram, right? We have a parallelogram. And this is some say U vector. Okay, let's call it something else. Let's call it R vector. And this as S vector. Right? So the area of this parallelogram, as we have learned from our school years, is the half of the magnitude of cross product of R vector cross S vector. Right? This is what we had learned. So S vector and R vector just needs to be, so these are right. So R and R vector and S vector just needs to be the vectors of two edges, right? And we take it we take its cross product and take its norm, and then we get the area. Likewise, for the surface patch, this S vector was similar to uh, this S vector is similar to sigma u du. Now I'll ask, why is this the case? The thing is, ideally, we have in parametric space u comma v, we have the length of this as du and this as de. After mapping, say with this du element is getting mapped, then it, as we recall from the multivariate calculus ideas, that this du gets mapped to sigma vector u du. Right, so it's just the partial sigma by partial u. So it's like sigma partial u. Likewise, this element will be mapped to here, right? So it was before it was dv, the length was dv. After mapping, it becomes partial sigma divided by partial sigma with respect to partial v into dv, right? That's so in a sense that sigma, partial sigma, partial v act some sort of a multiplicative factor, right? It just multiplies, it just amplifies it. So the area of this patch, so this patch we are considered to be sigma. So a of sigma will be equal to half. Again, I should not call this the complete. Okay, let's consider that to be very small, right? Let's consider them to a sigma. So a sigma is equal to half of uh, r vector is equal to sigma. I know I should just for this sake, right? Let's just be consistent here. So sigma u du cross sigma v dv. And since du and dv are quantities which are always positive in nature, we can, and also they happen to be scalars, so you can just bring them out. So it's du dv, right? So now when we try to determine the area of the entire surface S, right? So area of S is going to be equal to the integral of this patch, right? Sigma u cross sigma v over du dv, right? Over the u v, uh, the limits for u and v, right? So this is how we defined the so to speak, the area, right?
In this,
Area function. Yeah.
in this, like we can write like the first equation, that a of sigma which you have written. So it's
Uh-huh.
basically dA only, like differential a, right?
Yeah. So it's
And then you are
because
just
since,
integrating it.
yeah, since I'm considering sigma to be a patch, a small a small subset of the of this sphere, of this surface, right?
Okay, okay,
So
yes,
this is equivalent to saying dA of S is the
yes,
same
yes,
as area of the small s, right?
yes. Okay,
So
okay. Finally, you integrated it. Yeah.
yeah, finally we integrated it.
Okay, okay.
So now let's take a look at sigma u cross sigma v. So sigma u cross sigma v, right? So this is much like a Jacobian. It is, and it looks, in fact, it is a Jacobian, because Jacobian are always known to be positive, and it should be always positive in nature, or if not negative, it should always be non-negative. That's what I mean, right? So what we do is, I hope this half really comes. I don't know, because I think half is for a triangle, right? I think I was not prepared for this. So I think this half comes if you are trying to determine the area of a triangle. So I think in parallelogram, this should not be there because it was somewhat conflicting. So this half should not be there.
Right.
Right? Okay. So now let's just try to understand this fact here. So let's go back into some basic vector ideas, right? Vector identities. So one identity was that this is always defined as sigma u, the norm of sigma v, into sine angle between both of them, right? Angle between sigma u, comma sigma v. That's how we define a norm, right? Norm of a cross product. So it's like if you have a vector cross b vector, this is equal to a vector norm, b vector norm into sine of the angle between both of them into a vector which is normal to both, normal to perpendicular to both these vectors. And if you take the norm, then it's as if we are saying that it will be a cross b vector. This is equal to norm of a, norm of b into even norm of sine theta. Right? So in that sense, this should also be positive. So it's like something of on the positive. And provided that we are always taking it in a positive sense or taking the minimum area between them, then this will always be positive, right? For the dot product, we know very well that it will be sigma u dot sigma v is going to be sigma u sigma v into cosine of the angle between sigma u comma sigma v. And considering that theta, this angle between both of them are always chosen to be the smallest one, right? So what I meant to say is that if this is sigma u, this is sigma v, then we can either have this angle or this angle, right? I mean, in a way that you always have two choice bit of angles. So we only pick the smaller angle. That's what I mean here, right? So with this, what happens is, and you just take the magnitude of this such that this also will be magnitude, right? So with this, what we know is that we can always define this vector relation between sigma u cross sigma v squared plus sigma u dot sigma v uh, squared is equal to sigma u squared sigma v squared, and then you have sine squared plus cosine squared, so it evaluates to 1. Right? So with this, what we are able to do is this can be written as, this implies that sigma u cross sigma v norm squared is equal to sigma u squared sigma v squared minus sigma u dot sigma v squared. Well, ideally, this is just the magnitude, but yeah, it's just magnitude squared, right? And this, you know that the norm squared of a quantity can be written as the dot product with itself. Likewise for sigma v dot sigma v minus sigma u dot sigma v. And I think these terms would be familiar to all of us, that we have seen it somewhere. Right? So sigma u dot sigma v, we have seen it somewhere.
Capital E.
Right? In the first fundamental form. So which means that this evaluates to E, right? And then sigma v dot sigma v is capital G, and sigma u dot sigma v is
F.
F squared, right? So which means that sigma u cross sigma v, so to speak, the Jacobian is square root of this, right? So which means that A of sigma is equal to uv, and then just take first fundamental form. So you see that first fundamental form always appears in the picture whenever things related to lengths. I mean, any time we want to determine something which is related to lengths. So even area is related to lengths, right? In that sense. So which means that for any map to be,
Query at this point. See,
yeah,
this entire derivation is pretty good, but then I'm unable to understand that under what kind of the stretching the area would. I
area
mean,
would be.
area remains the same. I mean, under which phase or under which kind of the stretching the area remains the same, because whenever I stretch something, I mean, the common sense says that the area is going to change, isn't it?
Another thing is there is where a misconception lies, right? So the idea is that if you are okay, so there is where I would, of course, as we move along, we'll be talking something what is called as developability, right? So the idea is that whenever you look at the mappings, so we look at that this is the quantity which influences the, ultimately this is what is related to the area, right? Ultimately, this is the Jacobian determines the measure of area. So say, for
Yes.
example, you have this, I mean, let's go back to the previous figure. So we know that this surface was also obtained by some sort of a, say, sigma vector from this parametric space, right? Some, you know, something related to some lengths, some, right, from uh, say this distance, this is, so this length, let's call it as, uh, I don't know what to say. Let's just call it, say, capital U, the length of this, or maybe LU. And let this this length in of V, let's call it cap LV, right? And we make a mapping from this parametric space to sigma vector to this surface S, and from the same parametric space we have even obtained this, right? We can even obtain this. Let's call it sigma tilde. So it's essentially what happens is we can always use composition of maps. So sigma tilde is equal to sigma. Sigma was the base surface, which is this surface here, S. And then we are applying an isometry over that. So it's like phi. Right? So this is how we can define sigma relation between sigma vector and phi. Right? So which means that there is always some base coordinate space or the base parametric space from where we map to different surfaces. So all that has to be done is that this sigma metric, that this, the, what do you call, say, what happens? Say this sigma, right? So what we will do here is that this sigma vector, sorry, this phi is also a vector valued function. So all that we require is that say we have this matrix, say phi, and then let's call it as phi u, phi v. So not like that. Let's call it as, so this phi will be composed of two components, right? So this will be composed of two components, phi 1 and phi 2. And this will be function of uv, and this also function of uv. But since we are already mapped to another surface, right? So let's just call it sigma. Okay, let's just let it be like that. In just assuming that we are just hiding the parameters, the arguments to the function here. So all that I meant to say is that the mapping of the quantities here. So the in this case we'll also have Jacobian, right? So it will also be some matrix. And in this case, sorry, this was not just two valued, it will be three valued because we are mapping to from 3D to 3D, right? So it will be, okay, now I can write this more clearly. So the Jacobian of this mapping, so Jacobian of this mapping. So this is the mapping. and we would want to have a Jacobian of this. So the what do you call d sigma tilde will be equal to. So now we are mapping one vector element from d sigma from this surface here to this surface. So which means that it will go through, it will result in a matrix vector product. It has to matrix vector product. So what we'll have here is we'll have phi1 by phi x, phi2 by phi y, phi3 by phi1 by phi y, and phi1 by phi z. Likewise for 2 by x, phi 2 by phi y, phi 2 by phi z. Likewise phi 3 by phi x, phi 3 by phi y, and phi 3 by phi z. Right. So at best we can call this as, in a short notation, we'll just call it as this one is equal to some r. R is a matrix, this sigma. Now for the isometry to happen, right? For the isometry to happen, we want that the determinant of R must always be 1. So any mapping phi whose Jacobian has a determinant of 1 means that I mean, we can very much say that that isometry is a that particular mapping is an isometry, and this should be at all points. It should be all points, all x, y, z is an element of S for the surfaces. So that's how we would call this, because the thing is we always want the at least some sort of a length being preserved. Right. So I hope you are getting my point here.
Yes, I'm understanding it. Yeah.
Right? So this is how we define mapping. So, and ultimately we can always link it with the first fundamental form. So if Eg minus f squared is the same before and after mapping, then it implies that uh, the mapping is isoareal. Mapping is what we call as equiareal, like it always results in equal area. So that was the whole aim. And EF minus E square is the same. So for this to always be a strong condition, we can call that E, F, and G must remain the same. But I don't know. I have not explored further to what if the combination EG minus F square is the same but they are not individually the same. So I have not. I'm not very much sure about this. Maybe there is still I need to look at. So but this is just the strong condition are the same. Right? So this was the whole purpose of, say, isometry and all. Today we would come back to what we planned today, and this part we would move a bit fast because there is not much to imagine. It's all definitions and what you call operations. So of course I'll try to explain to the best I can. So today we are going to learn about curvatures and curvatures of surfaces. So first of all, what we learned from first fundamental form is it only gives us the length between 2 points. But we would want to know how much the surface is curving. Like, so for a flat surface, the curvature is always 0 everywhere, right? However, for a sphere, these are two extreme situations. For a sphere, the curvature is always non-zero, and it's always the same at every point. So it means that you can never travel on a surface without seeing curvature. The curvature is always there. You name it, you draw any line between any 2 points, you will always, the line will always, the curve will always have curvature. It will always have non-zero curvature. But this is not the case for cylinder. So say if you are walking along the generators, right? Last time we had discussed that cylinder is some sort of it's a ruled surface. So if you walk along one of the generators, then we would not distinguish. So like we would not be we would not figure out whether I'm on a plane or I'm on a curved surface if I'm particularly walking along a generator, right? So which means that there are curves on a surface which has zero curvature throughout. However, if you choose any other arbitrary path, then we come to realize that okay, it seems that the surface on which I am trekking, or if on which I'm or which I am trekking on or tracing, is a curved surface, right? But but you can still have certain curves in which the curvature happens to be zero. This is never possible in the case of sphere, right? So let's try to get some idea about uh, what I mean here. So you have this patch, right? And at every point you have, say at this point P vector, you have a surface normal and vector. And like the previous cases, let me blue. So we have some U coordinate lines, and for the others we have V coordinate lines. Right? So which means that at this point you have sigma V, and this is the sigma U.
I
So
have
U
one
varies
query.
this way, and V varies this manner. Right? Okay.
I have one query like
Yeah.
regarding the previous one.
Yeah.
So you told like if we move around along a directrix, then we won't feel the curvature. But like if the
Right.
directrix itself is a curve, then so it will be will feel the curvature will be there, right? It should be there. Na?
No, the thing is, we are specifically talking about cylinder, and directrices are always normal line. They are always lines, not curves.
Okay, okay, okay,
So directors are always straight lines, always. So if
okay,
we
okay,
move
okay.
along the director, then we would never have. So we would not be able to figure out whether we are curvature. However, a little, if we tilt even a bit little here and there, we can easily see that we are on a curved surface. So it's that straightforward.
Okay, okay, okay.
But for a plane, we are always, it's no matter where we go, we always see zero curvature.
Okay, okay, okay.
Right? Okay, so what we have known is we have this basis vector sigma u sigma v, and then we define something called as a normal to the curve, to the surface at point P, at, at a point P vector. Now, how do we define normal? It's like sigma u cross sigma v is the vector will always be perpendicular to both sigma u and sigma v. And what we do is we want the normal vector to be always unit normed. So just divide it by the magnitude of the same vector. And this we call as n vector. Now making some, let's try to understand it again with an analogy to making an analogy with respect to the curves. So we have this curve, right? So there was one way of measuring curvature was, say you have this planar curve. So you have this and say this is x and y axis. And any point you have, it makes an angle theta. So the local tangent vector at say point P vector here makes an angle theta. And any other little ahead, or say just a point which is slightly ahead, and I'm putting this just for exaggeration purpose. Let this tangent vector be aligned with d theta, theta plus d theta with respect to the horizontal plane. with horizontal axis, right? So what happens is the kappa, as we know, was the turning rate of turning. So it's like d theta by ds, provided the element, the distance between both the points is ds, right? And this was one way. Here we chose tangents. This is tangent and this tangent. But you could say, okay, this is fine. Can I not define it in slightly different manner? So you take the same curve. Let me just pull up the same curve, put it here. And at this point, this was the tangent, this is the tangent, and we are looking at normals, and this is the normal to this tangent, right? So this is what we call as the normal. And at this point again, we have this as the tangent and this as the normal. And what we can do is let's bring both the normals together. So it's as if you had this tangent here, which is making theta. So the normal is making an angle of theta plus pi by 2, because normal is inclined at 90 degrees with respect to tangent. Likewise, here again, what you have is the normal is like, let this be n vector of s and this be n vector s plus ds, right? So the tangent vector was making angle of d theta plus d theta. So normal is going to be just add pi by 2 to it, right? So it's like pi by 2 plus theta plus d. So the way we would see is, right? So the way we would say is we would have pi by 2 plus theta minus plus d theta minus pi by 2 plus theta divided by ds. So let's just look at this quantity. So it gives us pi by 2 cancels out, theta cancels out, and we see that, oh, we get the same quantity. Right? There's the same quantity. And here we are looking at the turn, or the what we call rate of turn of normal vector. Right? So we see that, okay, we can even describe the curvature looking at how the normal vector is changing. Right? I hope you understand this point, because this point is what this is how we typically use to determine the curvature for surfaces and all. We use this analogy. So in curves, we are looking at normals. We're looking at the rate of change of normal, I mean, of the tangent vectors. And in surfaces, we principally look at the rate of changing of n vector along both u and v coordinate lines. So it turns out that the values, the curvature given by any of these approaches is always the same. So what we'll do is we'll take the normal vector approach here. Fine. So you have this as one point. So at this point we had n vector u. So let's just call it u v. And at some point here, and let the distance be du along the u coordinate line and dv along the v coordinate line. So at this point here, the normal vector is going to be n vector u plus du v plus du v plus dv. So which means that again, in mind you that in curve we only have one curvature. In surface we have uh, three unique curvatures, right? So let's see why. We will have three unique curvatures. So v plus dv is equal to, let's do some Taylor series expansion. I hope it makes sense. Maybe just as of now, let's keep it like that. So this just to suggest that at sigma vector u plus du v plus dv, the normal vector is n vector u plus dv. And likewise for sigma vector u comma v, the normal vector is n u comma v. Right. So what I'll do is let's try to uh, define what we call as, so similar to what we had done for the surfaces, so for the curves. Of course, it was very ad hoc. So we were looking at fixing tangent one point here and doing some Taylor series expansion, and then we were looking at the same normal vector, considering the same normal vector at both the point, in a sense that fixing normal vector here and looking at how much the curve is turning with respect to with respect. What happens is in surfaces we'll use a similar approach, but I'm sure it doesn't give much sense. So say you have sigma u plus du v plus dv minus sigma u comma v, this dot n vector. Right? So it's like you take this point and look at the dot product with n vector. N vector you choose as the point at the point uv. So this just gives us an idea of that in the neighborhood of this p vector, or the point p vector, in this point p vector, how much the surface is turning from there. Now you'll ask, okay, what if it is a small, if it is a plane, if it is a flat plane, right? Then sigma vector u plus du v plus dv minus sigma vector u comma v. This is going to be some line in the plane. Right? It's going to be a line in the plane, or maybe it's a small line segment, right? Or maybe just vector in the plane. And you know the vector in the plane is always going to be normal. And if you take this part and then dot product with n, this is going to be 0. And this, you see, right? In the plane of there, what do you call, in the local neighborhood of any point, you are not turning away from the normal. I hope you, I mean, I hope I'm able to explain this thing. So you have this point n, this some another point here, and as you move from here to here, you see that you are the n vector, what do you call, any local, say, excursion from this point P is always normal. It's always perpendicular to n vector. So which means that in a sense you're able to see that there is no curvature, because you are not turning away. You are always maintaining 90° with respect to the normal vector for along any local excursion from this point. In a general surface, however, sigma vector u plus du minus comma sigma v plus dv minus sigma u vector dot n is not going to be 0 in general for a general surface, because in a general surface you will always have some sort of you'll always have some curvature. So what we do is, let's just take this thing du v plus dv is equal to sigma vector u comma v plus sigma u du plus sigma v dv. We are just using Taylor series expansion, right? Taylor series expansion. Taylor series expansion about u comma v, right? About sigma u comma v, sorry. So then we'll have the second order derivatives, which is half sigma vector u dot du into du squared plus half of sigma vector uv of sigma vector uh, uv du dv plus half sigma vector vu du dv plus half sigma vector vv dv squared plus higher order terms, du cubed, dv cubed. And since we know that sigma vector is a smooth map, because of which these two quantities, this and this, are going to be equal. So all that we can do is remove this part and multiply it with respect to 2. Right? So this will be 2 times. So it's just sigma uv plus sigma uv. And just delete this. This will be plus half of sigma vv dv squared plus the higher order terms. Order of du cubed dv cubed. Right? Now what we do is we wanted the value for sigma u plus sigma v, sigma u, I mean v plus dv minus sigma vector u comma v. This is equal to sigma u du plus sigma v dv plus half sigma uu du squared plus sigma uv du dv plus half sigma vv dv squared plus other terms. These are all right. Now we want to know the what you call the expression for dot n, right? This difference dot n. So what we do is we multiply throughout by n. So multiply throughout by n. Why not use a different color? N dot n dot n dot n. This also dot n, but anyway we can just ignore it, keeping the remainder term. Now what we recall is sigma u dot n vector. So n vector is always going to be perpendicular to sigma u. So this term is 0. Likewise, this is also 0. So we are left with is half sigma uu dot n vector du squared plus, let's call it half into 2 sigma uv dot n vector du dv plus half sigma vv dot n vector dv squared plus higher order terms. So what we can see here is that these terms, sigma uu dot n vector, this we call as L. This sigma uv dot n as m and this as n. Not to be confused with n vector, this is just n. So what we have is L is equal to sigma uu dot n, m is equal to sigma uv dot n, n is equal to sigma vv dot n vector. Sorry, this was n. I'm just using, these are just standard notations, so that's the reason I'm just using the same this particular letters to denote this quantity. So ideally what we would say is that this term here, in abbreviated sense, is equal to half L u squared. Let's take this as common, half as common, plus 2m du dv plus n dv squared plus higher order terms. And you recall that this quantity on the left, this quantity gives us an idea of curvatures in the immediate neighborhood of a point, neighborhood of a point on the surface, of a point maybe p vector on the surface. So which means that L, M, and N should give us some idea about what you call as the curvature, right? So the coefficients L, M, N. Now this thing is what is called as the, maybe I should write it nicely. This is called as the second fundamental. So this is called a second fundamental form.
So does this mean that the first is only about computing the length and the second one is only about getting the curvature? Or is
True,
there
true,
relationship
true.
in both? Okay.
Yeah, true. What happens is using the second fundamental form, you cannot get any idea about the distance. It does not compute distances. Because as we recall, right, when we are deriving, we can clearly see that it only gives us some sort of a local behavior of turning, right? So it's like how does sigma the how does right? So sigma u was the tangent. So any point, say again, let me take a portion of the curve of the surface. Right? So this was sigma u, and again at this point this will be the sigma u at u plus du. Likewise, right? This is sigma v at v, and this point will be, at this point the tangent vector is sigma v plus dv. Because the thing is this is u is equal to constant lines and this is v is equal to constant lines. So that is the reason I'm hiding other argument. So you can clearly see that as you progress along this line, sigma uu is what? Sigma u is ultimately it gives us the rate of change of sigma u with respect to u. Right? So it means it gives us how much this vector is changing with respect to the variation. So u is varying like this. So how does the vector u change with respect sigma? How does the vector sigma u change with respect to v u? And along this line, how does sigma v vector change along with v? Right. So it gives us some sort of the idea of turning. Right. You can clearly say it gives us a turning. It tells us something about the turning. However, but you'll ask, okay, it's turning, but with respect to what? Right? That's the reason we multiplied with n, with dot n vector. And dot n vector is always with this point. So just not to make things confusing. So this is the n vector that we are choosing as the reference. This is point p vector. We are choosing this n vector as the reference. So you can clearly see that it's turning with respect to this with this normal vector, right, at this point. So sigma uu dot n vector gives us turning along along the u direction, and turning this, and sigma vv dot n gives us the turning along this direction, and you'll have, since in general you'll also have cross coupling between sigma uv. So like this term will be, if you look at this from the top, then you would find that this is sigma u at u, and this is sigma u at u plus du. Right? So along this line, if you look at along the v direction, so you also see some turning, right? I hope I am able to make you clear. So
Yes,
if you
yes.
look, right, if you look from the top, then along v direction also you see that there is a change. So this results in cross coupling. So it is like delta sigma u by delta v, which in limits of delta v tends to 0 becomes sigma uv, right? So when you take a dot product with n, then it gives us a cross coupling between u and v directions with respect to the normal vector. So that is the whole idea. So you can now clearly see that this L, M, and N tells us about that. It does not give us the curvature. I must tell you in beforehand, it does not give us the actual curvature that we want, the value of the curvature. It gives us an idea about curvature. For getting the actual value of curvature, we'll move we'll move forward to be able to get that value, the actual value of curvatures. So L, M, and N are these are this is called a second fundamental form. Right, and I'll just write it down for the sake of repetition. N vector M is equal to this M actually sigma uv dot n vector, and then n is equal to sigma vv dot n vector. Right. So now we'll move forward to try to understand how do we get the actual curvature. So far we were able to find, okay, so at least we got some idea about the curvatures, and you can clearly see that take us again. I think things are best understood if studied through examples, right? So let's take this surface, flat surface, because it's easy to demonstrate why it's the case. So let's take a flat surface and recall that we could always have this as point P vector, and then this say A vector, and this is B vector, such that there is a 90-degree between them. So at any point, say this point, so let this call as the say some Q vector, right? So say any point P vector can always be sigma or P vector is equal to sigma u comma v is equal to Q vector plus A vector u plus B vector v. So these are like uv are the coordinates, and A and V vector are something like they are the basis vectors. And n vector, which is at this point n vector, is going to be equal to A cross B divided by norm of A cross B. And what you see is A and B are fixed vectors in a plane. So these are constant vectors, because of which n vector is going to be constant throughout. Now, when we take a look at sigma u, then this gives us A vector. Sigma u is equal to 0 vector. Likewise, sigma v is equal to B vector. And then sigma vv is equal to 0 vector. And the cross coupling, so the cross derivative, or the mixed derivative as we call it, sigma uv is equal to 0 vector. So which means that we can see that L is equal to sigma uu dot n is equal to 0. Likewise, even M and N are also 0. In a sense that we can clearly see that flat plate has 0 curvature, and that is reflected even in the coefficients. Even in LMN, you can see that it gives the values are 0, which means that it does. I mean, plane does not have curvature. You can clearly see just by looking at the coefficients of LMN. Right? That is the whole idea of what we are doing here, right? Okay, so now we'll move forward and talk a bit about Gauss map. So the Gauss map is, say we have any arbitrary surface, arbitrary smooth surface. Take this point P vector. This has the sigma u, this has sigma v, and the normal will be given by n vector. When you recall that normal vector is always unit normed, right? It's always has a value of 1. So which means that n vector is an element of S2. Now I'll ask, what is this S2? S2, right? So S2, in general sense, a slight digression again. So we define a space Sn. It is a collection of points X vector is an element of Rn. X vector is element of Rn plus 1 such that, I should call it collection of all those points Rn plus 1 such that the norm of X is some constant C, where C is an element of real, it's a scalar. So you see that if n is equal to, if n is equal to 2, then X vector is an element of R3, right? So which means that it denotes a sphere, right? I hope you are able to see this, or maybe let's start from the basic case. If n is equal to 1, of course, 0 makes no sense. If n is equal to 1, then we'll have S1 is equal to X vector is an element of R2, and such that is equal to C. C is an element of R. So which means that this denotes all those points in R2 space which are bounded such that their magnitude is always C. But because only in a circle we have only the periphery of a circle, always the points on the periphery has maintains the distance C from the center, right? From the origin, right? So which means that these are all points. So this denotes points on a circle, on circle boundary actually, right? Likewise, if n is equal to 2, then we have S2 is an element of X is an element of R3. Norm of X is equal to C. C is an element of real number, which is in a sense that it represents a scalar. And likewise, we have a sphere. Again, the distance or the radius of the sphere is C, and the S2 denotes all the points which are on the norm, which are on the surface of C, which are on the boundary of the surface, right? Which is right. So this was a slide diagram. So which means that n vector is always, because n vector is a unit, it's unit norm because of which it's constraint. So in this case, n vector is an element of S2, which is in this case it becomes X is an element of R3, such that the norm of X is equal to 1. It's a special case of S2, right? So and what we know, yeah.
So why this I mean, mod is equal to 1 and considering this as a special case? Yes.
Yeah, because here it could, this is for the case when C is equal to 1.
Oh, I see. Okay.
Right? In general, it is arbitrary C. And again, there is a constant that C is also, I should call it R plus and 0. So R plus is all positive real numbers and including 0. But 0 doesn't make sense, so we'll only have R plus.
Okay.
Right? So now I'll ask, okay, but what does Gauss map mean, right? So Gauss map is nothing, right? Gauss map says that to every point P, which is element of S, so this is S, to any point element of P, we assign a normal vector NP, right? So this is always to any, we have this particular NP. So this is the normal vector NP. P subscript indicates its point P. And you know that P lies, the NP is a unit norm, which means that at every point in the surface, we have this n vector. So all that Gauss map does is it maps any point So this is n vector here. So it maps. It's a map which gives us a mapping from the normal to a point p vector on the surface to a sphere, because ultimately all normal vectors belongs are the points on the sphere on the spherical boundary. So this will just be this here. I don't know whether it's perfectly spherical or not. Remove this for now. So x, y, z, this is a sphere, and so this is the going to be the normal vector np, and this is just a map. So this map is called as Gauss map G. So G will take a point p vector, and it will give us n vector at the point p. Nothing special. It's very simple looking. It's just we want to somewhat systematize even normal vector. What we mean by normal vector? Just by systemize. So this is S2, which means sphere in three dimension, and this is just the surface S.
So I have a doubt.
Now,
Yeah,
yeah, yeah.
what if say I so what this p here is? So I mean to say that what if I added del p here? Say then the g of p plus del p would be equals to what in terms of the n? So would it be, I mean, by the same amount, say n of p plus del p, or would it differ by some other amount?
I didn't understand. Can you please repeat?
Yeah, so my question is that what this p here is, because you computed the normal, I mean, for the point p, and probably you represented p as some area, I mean, some sort of an area kind of a thing, small portion kind of a thing. So my question is that if I move this, I mean, p slightly towards the right, so the normal vector will move towards the right. So then,
Okay,
to
okay.
which equation this n will move in this transformed figure over the sphere? I mean to say.
I see. Okay, so this P is just a point on the sphere actually. This P is just a point on the surface S. So you can have this Q vector. So when you apply this Gauss map to Q vector, which is a point on the surface, it will give us NQ. And this Q vector seems to be like this, right? It's like the normal vector is like that. So you can take it here. So this gives us, this is the NQ, right? It does nothing apart from this. It just maps. So what I'm able to say is that no matter wherever you move on the surface, Gauss map will always take you to a boundary of a sphere. So the normal vector will only be will always lie on the boundary of a sphere of unit radius. I hope you understood what I'm meaning. No matter wherever you go, right? The normal vector is always normed, and you can always bring this and translate this vector from here and put its tail at the origin, and wherever it intersects the or wherever it touches the boundary of the sphere, that is the unit, that is the normal field, normal vector, right? It does nothing apart from that, right? This will be some any arbitrary and r vector. So this is like you take any point, find the normal, and this seems to always lie on the surface of this sphere. I hope you understand what I mean. It's just what you call mapping of normal from on any point of the surface to the boundary of unit of a sphere of unit radius. That's it. It does nothing beyond that. That's what is called Gauss map.
Yes,
So
yes.
Gauss map is also called as normal map, because it only finds it gives the normal at every point. So you would ask, okay, how can I write it in functional form? Of course, you can write it in a functional form. So GUV is equal to sigma U cross sigma V divided by norm of, and which is the same as the definition of a, right? This is the same as the definition of a normal vector. So this is how you map. So this is just, it's a just way of saying that normal, it's just a map which gives us normal to any particular point on this surface. Nothing beyond that. It's just confusing by its name, but it's the same thing. It's just a normal map, normal vector map.
Yes.
However, the complexity lies to understand what we call as the differential map. So what you have is we now will go to understand what is called as Weingarten map. And I believe in surfaces, at least for us, what we are dealing with, its Weingarten map is little difficult to understand. To not, of course, it's easy to understand from mathematical formula, but we want to visualize it at we want to have some mental picture of what we are trying to devise here, right? So say maybe I'll remove this figure, draw a neat one, because that's what is needed. Oh no, something which shows curvature in slightly more detail. So something like this. We have this point, draw a normal. So there's normal vector. This is u comma v. The surface S. And last time, recall that we had understood something called as a tangent plane. So this is going to the tangent plane, for which the basis vectors are sigma u, sigma v, right? And then we have this normal, right? So this, so far so good. So this plane is also called as TPS because it is tangent to the surface S at point P, right? So that's what it means, TPS, tangent to surface at point P. The way we read it as tangent to S at P, right? Now you'd ask, fine, but what is going to go Weingarten map? Now take a look at n vector. So you recall that n vector was not unit normed, right? N vector is unit normed. So which means that n dot n is also 1. And if you differentiate it, right? Say you take differentiate it. And I'm not specifying with what parameter I'm differentiating. I'm just differentiating it. And so that it becomes some sort of a n dot dn plus dn dot n is equal to 0 because 1 is a constant scalar. And this you can, of course, commutativeness property of inner product gives us n dot dn is equal to 0. This is a very fundamental what you call, this is what we are going to use it here. So what does it say? It says that any change, this statement says that any change in normal vector is perpendicular 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 to itself, to normal. In that sense that any change in normal is nothing but dn vector is perpendicular to normal, which is n vector, right? That's, it has very simple, straightforward meaning. So let's, okay, but what does it say? Fine. So what we'll do is, recall in the previous page we had discussed about Gauss map. So I'll just draw that unit surface, unit sphere again. And maybe just pull it up from here, drag it down, slightly reorganize it. Yeah. Recall from the Gauss map, what we had done is we have this units normed sphere. Any this P is this is NP because it's normal at point P. So if we translate, it looks roughly something like this. It is NP vector. And this tangent was TPS. So what we can do is we can even have a tangent plane here. Or maybe just take this tangent plane, put at the origin here. And you know that all tangent planes pass through the origin. I should draw something like a parallelogram actually. So it's as if what you are doing is you are taking this tangent plane and just translating it. You are translating it and intersecting it through the origin of the sphere here. It was nothing but TP of S. We are just doing that. Right? These things are slightly confusing even for me as I try to understand it. This so it means that we are taking and translating it. Now, what happened is we recall that dn. So this dn is going to perpendicular, right? So dn. So this may be some other normal vector. Let this be some normal vector. Let's call it nq. And this is n dn vector, right? So dn vector is perpendicular to np. So which means that this dn is going to perpendicular to np, right? And which of course we know from here. We know from this definition here that dn plus this is 0. Now what we do is, since you know that dn is perpendicular to np, and even the plane, what you call the tangent plane is also normal to np, right? If you see things clearly,
I have
what
one
you call,
doubt.
yeah.
A same point P can, how can it has two like normal NP and NQ, like from same
No, so
point
this
P?
okay. This was just to uh, okay. I just maybe it will be some another normal. Just say this normal.
Okay. Now it is clear. Okay.
So it's just I just assume that I have translated it to make just to get an idea of what we are doing. We are just
Okay.
translating this
Okay.
vector and joining at the tail and to see what dn will in vectorially what it will imply.
So by translation, you mean like we translate this tangent plane to a new point Q. So like, is it like that or
Okay,
what?
what I'll do is I'll just remove from here. I think now things are fine, right?
Uh, yes. Still, like, what is DN? Like I'm
Okay,
unable to visualize what is changing here. Like,
okay. So dn is any increment in np, in any increment in normal will always be will always be perpendicular to the normal itself.
okay. Yes.
Reason why? Okay, I forgot. Okay, this mathematically this is how it should be. However, when you look at, even if you increment n vector, it still has to satisfy this property. It still has to get norm of 1.
Yes.
Right? It always has to satisfy that, because even if you are incrementing np, means we are just finding the normal vector field at a slightly different point in the neighborhood of the point p. And
Okay.
even
Understood.
if, right, so here it would mean like that. But if you're looking at the Gauss plane, so say here it was very simple. You just join this, right? This is like nq, and this will be the dn vector. Here it's straightforward to do. You can, because in Gauss map we are just bringing it to the normal vectors are just vectors which ends on the surface of this sphere. Fine. So far so good. Like we are able to see what is going on. So what I was trying to say that is you have this tangent plane for which NP is the normal vector and the increment dn is normal to NP. Right? I mean, graphically speaking, normal vector NP dn is perpendicular to NP and tangent plane is also NP. It's also perpendicular to NP. So meaning that NP is perpendicular to TPS and NP is perpendicular to dn. So this means that I can say that dn lies in TPS. I can say, right? I can say this, right?
Yes,
If not, if
yes.
I can say this, right, that this lies in TPS in the sense that you can always translate it, or I mean, or in a sense that these are like parallel, just to be. So
So,
dn vector is parallel to n TPS.
so does this mean that the existence of NP guarantees the existence of NQ?
What could you please repeat the guarantee? I mean, existence of.
Yeah, so the existence of NP. So if NP exists, then definitely there would exist a NQ such that uh, we can always find a vector dn and which is perpendicular to NP. But then for that thing we'll have to compromise. We'll have to find the appropriate TP TPS. I mean, so I
Okay,
mean,
okay,
so
okay,
my
okay.
so my question is that just because we are having NP here, so does this guarantee that definitely we are going to find a NQ in such a way so that we can find a DN which is perpendicular to NP?
Okay, okay. The thing is, here we are not looking at that part actually. We are not looking at existence of anything. Like just to clarify, we are only looking in the neighborhood of some normal vector and say that we are only wanting to understand how does the differential of n look like,
Yes.
right? So it's like the differential of n lies is parallel to TPS. So that's what we mean here,
Yes. Now it is well understood. Yeah.
right? So that's what we mean by here. So it's like dn is parallel to TPS. It's the same thing that you can always describe. Uh, Here you can always see that dn has no component along n vector direction. So which means that dn lies in TPS. That's very well evident because if you represent, you can always represent in terms of some alpha into sigma u plus beta into sigma v. You can always do that, right? For the differential reason. And if you have say gamma of n of vector, then this simply means that gamma is equal to 0 because dn vector has no component along n vector. Right. So this is the whole point of saying this thing. So which means that when you are finding a differential dn vector, all that we are doing is here it will look like that. And if you take it here, if in this case differential is dn was just something which was joining np and nq. Q is just some point in the immediate neighborhood of p here, and you have a tangent plane at this point as well. And so which means that so this tangent plane, so this point np is also called as g of p. So this point will be the where the normal np ends is called as g of p, right? And then the tangent plane at this tangent plane is t g of p because it's at point g of p, and then s squared because now the surface is s squared s2 and the point is gp. This is a very subtle thing here. So I hope you are understanding this thing. So what I'm trying to say is that n and dn vector lies in this tangent plane, which is tangent to S2 at point GP, and GP is nothing but the Gauss map of point P on S2 surface. I'm sure it will take some time to understand because it really took me quite some time to figure this out. It seems very easy, but to visualize it. So we can clearly say that TGP S2 is the same as TP of S. Reason is because we can clearly see that dn lies in TPS, and when you look at in the Gauss or in this on the unit sphere, we see that dn vector is just a vector which is in small infinitesimal vector which connects np and some point in the neighborhood of p. So this is the conclusion of this. So the ideally now I'll ask, okay, but what are you talking about? Where is the differential of Gauss map coming into picture? So all that we know is the differential of the Gauss map maps TPS to TGP of S squared. So this will be like the script S, and this is S squared, and this is the same as DPG TPS to TPS, because we are able to show the equality of both these tangent planes. So speaking, we can call that the derivative of the Gauss map is a linear map from the tangent plane of S to itself, because we are just mapping tangent plane to tangent plane itself. So that is the whole idea of this, what do you call, of this the derivative of the Gauss map G. So once we have found out what what is the domain and what is its image, now we can define what we call as the Weingarten map. And Weingarten map is nothing, it's very straightforward. Weingarten map, simply speaking, it's just WP means Weingarten map is at point P of surface S is nothing but just the minus of DPG. It tells nothing else. So did you understand? I mean, where I was able to explain this thing somewhat in a comprehensible way. So the Weingarten map is nothing just the minus of derivative of G. And since it maps the tangent plane of S to itself, which means that WPF, this is just it's a tensor, because it maps vectors to vectors. It maps vectors lying in TPS to vectors in TPS itself. Right? So it's a map, because I mean it's a tensor map because it relates vectors to vectors. So that part I believe was somewhat understandable, if not very much, but that's the whole role. So it's like you have some vector here, some vector here, some vector here, and this is the Gauss-Weingarten map. Now let's try and understand what this WPF, how will we write this map?
Like I have one doubt.
Yeah.
So like in that above figure, if you can go, then that sphere, yes, this one, the Gauss
Yeah.
mapping of point P. So
Yeah.
like in this dn, the differential of the derivative of that normal dn is lying in that dgps square plane,
Yeah.
and then there is one point like tps.
Yeah.
So like
This
it is.
TPS is not point.
Yes,
It's
yes,
a
yes, like
plane.
tangent, yes, yes, yes. So that this plane,
Uh,
so like it is visually clear that these two are like parallel to each other, but it is not clear as to why these both are equal. That this is like I am confused here. Like
yes. Okay. That's the reason I was trying to make things. Maybe I was not able to properly make you understand. The issue is, say, in the local neighborhood of any point P, you always have three basis vector. You can always have, say, sigma u, sigma v, and n vector, right? So in any R3,
yes,
to properly define any vector in R3, you require at least, I mean, not at least, I mean, for complete description, you need only three basis vector, right? Three only
yes,
basis vector.
yes.
So sigma u, sigma v, and n vector, they represent three vectors. So which means
Okay.
that it's like basis vector locally.
Yes.
Right? So it means that, and you are dealing with, we can always define, why not have even n vector, dn vector, we can represent it some sort of a, this way, right? We can always represent that since we require only three and dn vector is a vector. So we can clearly represent in sigma u, sigma v, and n vector,
Hmm.
right? We can represent
Yes,
it.
yes.
However, what you see is if you take dot product with dn with n, then this term alpha into 0 plus beta into 0 plus gamma n into n is 1, right? So
One.
it's 1.
Yes.
But you know that dn dot n is 0. So it means that gamma is 0.
Gamma must be zero. Yes.
Yeah, which means that dn vector is only alpha sigma u plus beta sigma v, right?
Yes.
And you also know that TPS is a collection of any points, say something else. Let's call as TP is any points is equal to say m comma n, such that I think I should say any x vector such that x vector is equal to m sigma u plus n sigma v.
Yes.
But you see that they are the same thing.
Yes. Yes. Yes.
So which means that dn vector lies in TPS,
Understood. Understood. Yes.
right? So that
Yes.
is
Yes.
what we mean here.
Yes.
So that was the whole goal too. And once we know the Weingarten map, we know what it means, how it represents. So now what we can do is let's try to understand Gauss-Weingarten map. As of now, this is in abstract form. This is just abstract form because all we know that is a mapping. It only maps, and it's linear because of its very nature. Because differential is linear, right? D by dx is a linear operator, right? Now I'll ask how come it's linear? Because for linearity, all that you require is alpha into u plus beta into v is equal to du by dx plus beta dv by dx for alpha and beta constants, constant scalars. Right, this is how we define a linear operator. So even the differential operator is linear. And because of which, since Weingarten map is nothing but just the minus of the differential operation, because of which the Weingarten map is also linear. right? So it's linear. And you know that any linear map can always be represented in terms of a matrix vector product. However, so far we only have the abstract form. So our goal would be to know to represent W, WP of S. We want to represent this in some sort of a matrix form. Now what we do is, what we will do now is that, you know, that WP of S maps vectors, or maybe I'll just call it vectors, in TPS to vectors in TPS, right? This we know very well. So which means that if we apply WP of comma S over any vector, say V, just not to confuse, let's call it W vector, is equal to some delta into sigma U plus gamma into sigma V, right? Because, and where W vector is also an element of TPS. So which means that we can have WP of S is equal to, let's have W as alpha sigma U plus beta sigma V is equal to delta sigma U plus gamma sigma V. This we know very well, right? So far so good. Now you'll say, okay, why not special cases? Let's look at special cases because this is linear operation. Linear operation. This is going to be some linear operation. So why not look at special? Let's look at special cases. Let us look at special cases. The special cases means, number one, why not take W to be what? To be sigma U itself. Then in that case, the Weingarten map is equal to sigma U is equal to, now, like Weingarten map is, it has some abstract form, but you know that it's related to something else. It was related to the derivative of Gauss map. Right? So this is equivalent to saying that I want to vary sigma U and I want to vary it along certain directions. And let's call it as, so sigma U is the argument. So I want to look at d by du of g of sigma vector u comma v naught at u is equal to u naught. So I'll ask, okay, why this? Where are we moving here? The issue is because I'm looking at just this part. I'm looking at WPS. What we are doing is I'm wanting to vary. Look at the Gauss-Weingarten map of sigma u when, and you know that sigma u is along u coordinate line, right? It's along u coordinate lines. So it's like it's along this, like it's u is varying here and v is equal to v naught. So I'm looking at the variation of the Gauss map along this particular line, along v is equal to v naught, and where u is varying, right? U is varying in this fashion. So that's the reason I'm looking at derivative. I can see that it's equal to dg by du at sigma u vector, sigma vector of point u. So this is point u comma v naught, where u is varying and v is u naught, u is varying and v naught is a constant. this at u is equal to u naught. I just want to look at how the Gauss map is varying at this point, because that's what we imply by looking at all this. I'll just write some things to make things clearer. I believe I'm just creating confusions. So WFP of S sigma vector is equal to change in sigma u along u coordinate. That's what it means, simply speaking. And WP of S sigma V equals to change in sigma V along eh, along say V coordinate lines. V coordinate. Right? This is just to say, because we are choosing, so the map is defined in this manner. So that's the reason I'm writing the definition. So you must interpret the definition of the map to be able to understand it. Like it's this how we are defining it. That's the reason look at the definition only. Now you all for this case, you know that Gauss map is nothing but the normal vector. So n vector of sigma at sigma, because this point is sigma vector u comma v naught at u naught, u is equal to u naught. So you can just write it as n parcel n, but it's like as I should use this parse. Okay, since we are allowing, okay, we are not allowing. So it's we can write clearly as n vector u at u naught v naught. This point is u naught v naught actually, right? So see, right? So which means that if you take Gauss WP of S sigma u, this gives us n u u naught v naught, right? And then if you choose the special case where sigma is equal to sigma v, then WP of S sigma v is equal to nv sigma u sigma sorry nu, this is also be sigma of u naught v naught, and here also sigma of u naught v naught. So we have found some special choices. So this we have found, and so it will of course be minus. So I'll put it minus here. This will also be minus because it's derivative, it's negative of the Gauss map, negative of the derivative of Gauss map. So I hope what I hope I'm able to make things understand, because these are the definitions. So we must remember it the way the mapping was defined. So any other W vector, any arbitrary sigma u plus beta sigma v is nothing. You just pass it sigma, it's W vector. So 4 where alpha and beta are scalars, then this will be nothing but minus. So it's like WP of S alpha sigma u plus beta sigma v. This is going to be alpha WP comma S sigma u, because these are linear maps, plus beta WP comma S sigma v, and then you know the rest of the thing. So it's like minus alpha nu plus again minus beta n v, right? So now you can clearly see how we had defined. So this is how the relation will be for any general the Gauss map. So you can clearly see this is vectors. Now this is a vector, right? WP of is gives us a vector. Now you'll ask me, of course, you would have another question. You'll ask me, but you say that the vector should lie in TPS. Is it lying in TPS? The issue is, let's see, n dot n was 1. Take its derivative with respect to u. So it becomes n vector dot nu. is equal to 0. So this means that any vector lies in TPS or lies in the span of sigma u, sigma v. Likewise, n dot nv, when we differentiate this with respect to v, this is 0. So even nv lies in the span of. So ultimately, this quantity also lies in TPS. So I hope I am able to make this thing clear.
Yes, it is kind of clear.
Right? I mean, so you say that the Gauss-Weingarten map is mapping to TPS. So we took a vector in TPS and we could map it to TPS.
Yes.
The only good thing is for operational scenarios, we don't need to memorize all that. Operationally, we are not looking into this. We only look at how do we define a curvature. That's what we are looking into. We are not looking into all of this. So that is the good thing here. So in a sense that we can start talking about curvatures now itself. So we could understand somewhat Weingarten map. Now let's look at how we define the Gaussian, all the curvatures. Curvatures, Gauss, mean, Gaussian curvature, sometimes also called as Gauss curvature, mean, and principal curvatures. Fine. So let's define what is Gaussian curvature. Right. So let's define. So Gaussian curvature is defined as K is Gaussian curvature is equal to the determinant of Weingarten map W. That's it. Straightforward. It's as straightforward. Mean curvature H is nothing but half of trace of WPS. It's as forward as. So once we have Weingarten map, we can always determine Gaussian and mean curvatures easily. However, the thing is we still have not represented, right? We still did not represent W. So far, this Gauss-Weingarten map, the Weingarten map is still in an abstract sense, right? It's still in abstract scenario. So even now, the WP, we do not have a clear perspective. All that we know is WPS is a matrix. It can be represented. So we can represent in any basis. If we represent in any basis, then what we will have is a vector, a matrix. And since we are looking at surfaces, so surfaces are parametrically speaking, they are in 2D space. So we'll have A, B, C, D. This will the entries of 2 cross 2 matrix. So this is the representation in any basis. In some basis, maybe I'll just write in representation in some basis. Then you'll have ABCD. Once you have ABCD, then like K is determinant, right? Determinant of, I'll call it this as omega, the delta W. So determinant of matrix W is nothing but AD minus BC, and mean curvature is determinant of is half of trace of W. So this is A plus D by 2. Right. So now we know. So we were able to define this. Now let's represent now. So let us represent. Let us find a matrix representation of WP, S. That's what we are going to look at now itself. Right. So from the previous, what do you call previous our discussion, we knew two things, at least one particular property of WPS, which was that WPS, I can always drop PS because provided that it's understood, let's only call it W. So W, which is an operator, if you take an argument of sigma u, then it gave us minus n vector u, which is partial. It's like derivative of n with respect to u. We also knew that we could also derive this, that sigma v, this gives us minus n v. Right? So we could do this at least. Now I'll ask, okay. So
one thing,
yeah,
before this, you have defined like Gaussian curvature and mean curvature.
huh.
So, but like you have not yet told about principal curvature.
Yeah, so principal curvature we'll look at after this. So maybe
Okay, okay, okay.
why not do it right away? Okay. So
Okay,
principal
okay.
curvatures are the eigenvalues of WPS. That's it. Nothing more. It's principal curvature eigenvalues of WPS. Right. So we understood that Gauss, mean, and principal curvatures. So what we can say is if principal curvatures are kappa 1 and kappa 2, say kappa 1 and kappa 2, then mean Gauss curvature K is equal to product. The determinant of a matrix is equal to the product of eigenvalues, right? So it's just the product of eigenvalues, and mean curvature is equal to half of kappa 1 because the sum of eigenvalues is the same as the trace of a matrix. Right, so we could relate both of this. And here what we see is that even if the signs are switched, kappa 1 and kappa 2 are switched, K doesn't change, right? So if you take kappa 1 to be minus kappa 1, kappa 2 minus kappa 2, the product is always kappa 1, kappa 2. So it means that Gaussian curvature doesn't care about this. So you will say, okay, but how is the sign changing? The sign is changing because how we choose. Sign of kappa 1, kappa 2 depends on the choice of n vector, the normal vector. So even if the direction of normal vector is changed or the sign is changed, K does not change. And that is one of the reasons it is called as intrinsic curvature. It never depends on the choice of n vector. The choice of the sign of n vector. It always is invariant. However, H depends. So H depends on the choice of what you call. It depends on the choice of n vector. On sign of n vector. And that is one of the reasons it's also called as extrinsic curvature, like curvature which depends also on how we choose parameters or how we choose the signs of some quantities using which we are able to determine the curvature. Okay, returning back here, we want to find a matrix representation. Once we understand the matrix representation of WPS, then I believe surfaces is almost done. Like there is nothing much left then. So you saw that W of sigma U is equal to minus NU and W sigma V is minus NV. So
One more thing.
yeah,
So like if we in general if we have a surface, so
uh-huh.
like you are talking about choice of curvature. Sorry, like choice of normal vector for
Yeah,
that surface for any
yeah,
point. Then generally if we have a closed surface, then generally we take it like a vector which is kind of outside, pointing outside the surface, right?
yeah.
Is
The
it
thing
like
is, if
standard
you have
convention or something?
yeah, yeah, once we have a closed surface, any surface, we still do not know how to choose it. We only know the general direction of a normal vector. We do not know which sense are we talking about. As an example,
Okay.
say you have this surface and let this be sigma u and this be sigma v. Then sigma u cross sigma v, right? Can be say this, it gives us n vector.
Yes.
However, you could also have changed the parametric sense because it here it's assumed that it's right-handed coordinate, or it's assumed that this is it should give like that. So however, if you choose a parametric space in such a manner that what if it's sigma u cross sigma v cross sigma u, then it's going to minus of sigma u cross sigma v, right?
Yes. Yes.
It will be minus n, so it's like
Hmm.
downwards. So the thing is, you only know normal vector to signs, only up to plus minus n we can know. So
Okay.
we
Okay.
always have duality in choosing, and we choose one and then keeping that sign as the reference, then we determine the normal points at every other point likewise. And that is the reason where we had talked long back about what is called as orientability of a surface. Because this orientability always deals with how we choose the normal vector. Once we choose it, all the other points must also follow the similar behavior, the normal vectors at every other point. If it does not, then that surface is called as non-orientable. Now you'll ask me, give an example. Example is Mobius strip. So Mobius strip is not an orientable surface.
Okay.
So what you'll see is you start determining normal vector from one side. And as you traverse along the Mobius strip, you'll find that at the same point, you are reaching by taking the whole loop. So for example, say, of course, I don't know how to clearly draw a Mobius strip. It's just that half lies, I had half lie. So you say in this case, you have fixed n vector like this. And you just traverse this, traverse along some particular center line, some other color just for representation purpose.
Yes, it will invert itself after
Right?
one.
And then you will
Okay.
invert
Okay.
and you
Yes.
return to the same point and you'll see normal
Opposite
vector is like
direction.
that
Yes. 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 Yes.
at the same point.
Yeah. Yeah.
You'll say how
Correct.
it is possible because the thing is this surface by it's very fundamentally it's a non-orientable surface.
Okay.
Right? So that is the thing. Yeah. Okay, coming back here.
Hmm.
So what we saw is we could Weingarten ma'am, this one of sigma u is minus nu, sigma v is nv. So which means that we can write minus nu in terms of sigma u plus b sigma v, because right because we know that nu is perpendicular to n, which means that it can always be written in TPS in it can be represented in TPS. So I'm using a and b as the coefficients. Likewise, you can have minus nv is equal to say c sigma u plus d sigma v. The reason because nu nv belongs to TPS. That's the reason. So what we do now is take 1, this is 2, dot product of 1 with sigma u. What happens is minus nu dot sigma u is equal to a sigma u dot sigma u plus b sigma v dot sigma u. This means that minus nu dot sigma u is equal to a, and this is the first fundamental form, first coefficient, so ae, and this is the second fundamental bf. Now slight digression. We want to find the quantity on the left, which is this thing here. So one thing what we know from the definition is that n vector dot sigma u is 0. This we know very well, right? Since n vector itself is sigma u cross sigma v divided by norm of sigma u cross sigma v. So of course dot with sigma u is going to be 0. Now differentiate both sides with respect to u. Then what happens is nu dot sigma u plus n dot sigma uu is equal to 0. So far so good. What you can say is this, we know this is familiar term to us because sigma uu dot n was the first coefficient of the second fundamental form. If I can scroll back, right? See, right? This is sigma uu dot n, which is L. So which means that this is L, which means that L is equal to minus nu dot sigma u. So which means that this implies that L is equal to AE plus BF. Right? This part is understood. Now, likewise, what we'll have is sigma n dot sigma v is equal to 0. Differentiating with respect to v gives us nv dot sigma v plus n dot sigma vv is equal to 0. And n dot sigma vv was n. So this implies that n is equal to minus nv dot sigma v. So this was n, and for n we have two choices. We have n dot sigma u is equal to 0 and differentiate with respect to v. So we'll have nv dot sigma u plus n dot sigma uv is equal to 0. This is m, so therefore m is equal to minus nv dot sigma u or minus nu dot sigma v. It's like you have two possibilities. So far so good. Now we take dot product of 1 with sigma v. Then what we have is minus nu dot sigma v is equal to a sigma u dot sigma v plus b sigma v dot sigma v. So this is equal to this is equal to f, this is equal to g, and this is equal to, since this is a cross, right? It's a cross, I mean, there is a cross term here, so which means we can call it m. So we'll have m is equal to af plus bg. So this is one such, sorry, m is equal to af plus bg. One equation, this is one more equation. Now let's repeat for the same with for b, for 1, for sorry, equation 2 with sigma u. Then what we have is, just pick up this, pick this up, put it here. Dot with sigma u. This implies that minus nv dot sigma u is m, sorry, m, just m, scalar m, and then c E plus df. Likewise, take this, right? Sigma v implies that n, because it's minus n dot n is equal to c f plus d g. So overall, we have 4 equations. And here, what are unknown? Unknown is, in all these cases, A, B, C, D are unknowns, because they are coefficients which we need to determine. So A, B, C, D, we have 4 unknowns, 4 equations. So what we can do is we can write this in a matrix-like form. So let's we can write it in terms of a matrix-like form. After hit and trial of rearranging, we can write it to a nice form like this. We'll have A, we'll have matrix into matrix product is equal to matrix as well. So we can write this will be A, B, C, D. Right. So it'll be okay. So this will is A, B, C, D. A, B, C, D. It's all about arranging. How do we arrange things, right? So this will be E, F, F, G. This is L, M, M, N. Right? So, and this we can call a matrix. This we can call as F script F. We can get F1. And why am I using the subscript N1? Because this is matrix of coefficients of first fundamental form. And this matrix we'll call it as script 2, F2. This is because it's a matrix of coefficients of second fundamental form. Now you'll ask, what is this? This is nothing but representation of Gauss-Weingarten map in sigma u, sigma v basis. Because we said, right, that all that we want is to represent W in some basis. Since we have liberty to choose basis, we have chosen the most convenient one, which is sigma u, sigma v basis. So all that we have is A, C, B, D at A, C, B. Is this matrix is going to be F inverse F2. Right, so this brings us to 1 by the inverse of F1 matrix is EG minus F squared, by the look of this, into G E minus F and L M M N. And we can, of course, make it more complex and just multiply it with whatever we want. So GL minus, so say LG minus MF. So it will be mg minus nf and minus lf plus me, and then minus MF plus NE. So AC, BD. And the rest we know what to do, right? So Gauss curvature K is equal to determinant of ACBD, and this comes out to be it's LG minus MF into minus MF plus NE minus mg minus nf into minus lf plus me divided by eg minus f squared. So it's determinant, right? So every term is it's like every term is divided by this, so it's like f squared. And after lots of simplification, it can be written in a very neat form: ln minus m squared by eg minus f squared, right? You see, so it's like the determinant of f2 divided by determinant of f1. It's as simple, very clean expression we have. For the mean curvature, h is equal to we can write Lg minus 2mf plus Ne divided by 2Eg minus f squared. This is also a nice expression. And about principal curvatures, you already know what to do. It's like
Yes.
right? It's like A, B, C, D eigenvalues. Eigenvalues of, they have some kappa 1 and some kappa 2. Yeah, so this is what the different curvatures are. We would be solving maybe 2 problems max and talking a bit about normal and geodesic curvatures. And after that, we would start in the next session. So now what in next session do we expect? Next session we'll have, first of all, normal and Gauss curvatures, normal and geodesic curvatures. And 2, we'll start discussing about rod theories as much as possible. This is for the next session. That's what is planned. Okay, so I'll just stop recording.